Hello friends, welcome back. In this video, I am taking three important examples on double integration, and I have attached a link of my previous lecture explaining the theory of double integration and few important examples. So here I am with few more important examples. So in this video, we have to evaluate double integration. So first example, let's see first example. So we have to evaluate double integration 0 to 1, 0 to y of this function with dx and dy. So let's begin the solution. Let I is equal to this integration. Now we have to decide which integration is for which variable. So the integration having variable limits and the variable is y in that integration, so that is for x. So here I have decided that this integration is for x and this integration is for y. The constant limit is for y. So after deciding the integrations, we will start the integration. So I is equal to 0 to 1. So in this step we are solving the constant integration in the end. So we will solve with respect to dy in the end. So first of all, we will solve with respect to x because x is having variable limits. So I have taken all the terms in x, dx and its integration in one bracket, and then I have solved it. So integration of x is x square by 2 and its limits are 0 to y. So let's put these limits. So after putting the limits, instead of x you have to put y, so it becomes y square upon 2, and when you put 0 instead of x, everything is 0, so no value for lower limit, and this thing is as it is here, y dy. So this 1 by 2 is outside here, 1 by 2, and y square into y is y cube. So this y square and y is y cube. So you have to integrate y cube. So you have to integrate y cube with respect to y from 0 to 1. So integration is this. Answer is 1 by 8. So let's take second example. So we have to evaluate double integration from 0 to 1, one more integration, same limit, and the integrand is dx dy 1 plus x square 1 plus y square. So let I denote this integration by I. So this is I. Here the integrand 1 upon this thing, we can separate it. They are already in variable separable form, and one good thing is the integrations is a constant. So I can separate my variables, the integrand and the integration sign also. So here I have done the separation part. This is possible because the integrands are ready to separate and the integrations are constant limits. Integrations are with constant limits. So I have separated x and y. So you have to solve this. This is the standard formula of tan inverse. So integration of dx upon 1 plus x square is tan inverse x and the limits are from 0 to 1, and the integration of dy upon 1 plus y is tan inverse y. So after putting the limits, we have this step. Tan inverse 1 is pi by 4 and tan inverse 1 is pi by 4. So this is 0 and this is 0. So we are not counting this and this. So the final answer, the value of this integration comes pi square by 16. So here we have one more important question. So we have to show that double integration 0 to infinity of this integrand, it comes pi by 4. So one good thing is the integrations is with constant limits. So no, we cannot separate it, they are constant. I have to use substitution because this x and this x square, the derivative of this x square is x, 2x, which is present here. So we have to adjust 2 here. So let's begin the solution. So let this integration be I. Obviously I will try to solve with respect to dx first, because x square, its derivative is in my integrand. So I have separated x in one bracket, all the terms in x in one bracket. Then I have done this substitution because I want this exponential to be free from x square. It's very difficult to integrate e raised to minus x square. So to make that easy, that integration, we have x here. So put x square is equal to t, differentiate it. So we have 2x dx is equal to dt, and finally we have x dx is equal to dt. So x and this dx, they both will give me the value dt by 2. Now let's see what happens to the limits. My original variable x, I have substituted it by some dummy variable t. So what happens to the limits? So when x is 0, t is also 0 by this relation. When x is infinity, t is also infinity. So there is no change in the limit. Let's move further. Let's put all the values in that bracket. So integration 0 to infinity as it is. So inside that bracket, no change in the limits, 0 to infinity as it is. So this x and dx is dt by 2. So this dt by 2 is that x dx. And this x square, I have written t. This thing is as it is. Since we are integrating with respect to x first, and in this bracket my y will be constant for a while. So this bracket is constant for a while. Once this bracket is solved, I have to solve with respect to y. So I'm treating y terms or the functions constant here for a while. So let's solve this. So I've written that 1 by 2 outside of that integration, and the integration of e raised to exponential function is itself, but I have to write that constant in the denominator. So I've written minus 1 plus y square, and the limits 0 to infinity. Because I'm integrating with respect to t, I have to write that 1 plus y square and with negative sign in the denominator. By this rule, e raised to minus 8t dt is e raised to minus at upon minus a. Okay, so now it's time to put the limits. So I have to put these two limits at the place of t. So this thing and this thing has nothing to do with the limits. So denominator is free from limit. So I've written everything outside that limit box. So e raised to instead of t, put infinity first. So e raised to minus infinity. Then put 0. So it is this. We know that e raised to minus infinity is 0 and this is 1. So we have minus 1 in that bracket. So simplify this whole step to get this. Again, this is very standard integration. That's a formula of tan inverse y. So tan inverse infinity, tan inverse 0, pi by 2. And here's the answer. So we have to show that this integration is pi by 4. So it comes pi by 4. Thank you so much.